Welcome to this video. In this exercise, we're going to revisit the baby weight dataset. We have used this dataset before to create a linear regression model predicting the baby weight as a continuous value. In this exercise, we're going to use a decision tree, a classification tree, to predict the baby low weight, which is a binary variable, either 0 or 1. So a threshold was used to classify babies as low weight or normal weight, and most likely they used the value of 3,000 grams as a cutoff. Okay, so what we're going to do, we're going to create a classification tree based on some features, including the mom weight, premature labor, hypertension, and irritability. We're going to try to interpret the tree, and then we're going to try to decide whether the tree is doing a decent job or not, and then we're going to add 2 more variables to see if we can improve the performance of the model. So let's read the data first. Next, what I am going to do here, I am going to select the feature matrix and the target array. So the feature matrix are going to be the mom weight, premature labor, hypertension, irritability, and the outcome array is the baby low weight in this case. That's going to be my X and my Y. The second step is to create the model itself. So I'm going to create a decision tree. So it's going to be a decision tree classifier, and here I have the option of adding some hyperparameters. I'm not going to change the default, so I'm going to keep it as is. The next question is to basically either split the data or not. This again depends on whether I'm building my tree for explaining the data or for predicting the data. I'm going to assume that the target application for this decision tree is to make prediction. In other words, I'd like, given all of this data, to be able to predict whether the baby will be low weight or normal weight. So I'm going to use the function train test split in order to split my data to training and testing data sets. So this function will give you back the four variables, the feature matrix, and the target outcome for both the training and testing data sets. So I'm going to do yTrain and yTest. I'm going to call the function providing x and y. I'm going to provide the test size to be maybe 75, the training size to be 75%, because I want to use most of my data for building the model and just maybe save 25% for testing purposes. So the parameters that I want to set here is the train size, and I'm going to make the train size to be 0.75. So train size will be 0.75. Okay, so now I've got my training and testing. So if you take a look at length x or x.shape here, you can see that we initially had 189 observation, but if you take a look at the training data set, it only contains 141 observation, which is 75% of the original observations. Let's make sure the shape of the training target vector is 141, which seems to be the case. So then we are good to go. We can fit the model, fit the decision tree by calling the function fit and providing both xtrain and ytrain here. That's the decision tree. And we actually can go ahead and print the tree if we wish to. I'm going to use the function export text. Decision tree, feature names should be the columns of my x, and that's the decision tree. Again, you take a look at this decision tree, it's humongous and it's doing so many decisions to get to whether the baby is low weight and high weight. That's something that probably we can improve on if we want the tree to be more parsimonious. So let's revisit this, but we need to first assess the goodness of fit of the tree. Well, we splitted the data, so we want to make this assessment based on our training data set. Because if we do it for the, testing data set, this has to be ytest, excuse me. Okay, so we need to do this on the testing data set, Because if we do it on the training data set, we're going likely to get an overestimate of the accuracy. Let's actually do this. So I'm going to assess yFit test train to be D3 predict of X train. And then I'm going to assess the accuracy score in between the Y train and the yFit train here. And that's almost 90%. I can also do the confusion matrix. That will give me more fusion matrix. I need probably to import this function. So I can assess my confusion matrix, and it's kind of saying that it's most confused mixing the second class, like babies with normal weight, to being baby of low weight. Okay. So that's that, but again, this is kind of deceiving ourselves because we are testing on the same, we are evaluating the accuracy on the training itself. We're going to do it now the right way. I'm going to do yFit test rather than train by predicting the X test. Next, I'm going to assess the accuracy score in between the yFit test and the Y test. Because again, the tree hasn't seen this data. This data has been saved, kept apart for testing purposes. And now we are at 70%. So we should expect in real-life applications, when we use this decision tree for classifying new data, that we're going to make a mistake 30% of the time. If you take a look at the confusion matrix, now you can see that most of the confusion is happening in the first class when the baby is low weight. We're confusing it a bit often, but it's the other way around. When the baby is normal, we are often confusing the baby to be low weight. Okay, so now what we're going to do, we are going to add more features to the feature matrix. So specifically, we want to add smoked and raised to the feature matrix. And I'm going to use the function getDummies to convert these two categorical variables to a set of dummy variables. So again, here you can see that we've got race black, race other, race white, and race smoke non-smoker, smoked smoker as extra variables. Well, next I'm going to add these variables to my decision tree. So I'm going to get the X and the Y again, but this time from data 2, and I'm going to add to the feature matrix race black, race other. I'm not going to add white because if it's not a black or other, it's white. It's kind of redundant. It will not change the model fitness anyhow. And I'm going to add only smoked smoker. I can either choose non-smoker or smoker. I think smoker makes more sense because it's usually what people are looking at when they looked at whether the person is smoker or not. So that's my X and this is my Y, and what I am going to do now, I'm going to repeat the same steps here. I'm going to resplit my data. I'm going to create, well, probably I need to recreate the decision tree, so that's important here. And then I'm going to fit the tree using the training dataset. And I'm going to predict using the test dataset. Next, I'm going to take a look at the accuracy score. With the accuracy score is now has decreased to 62%. And we can take a look at the confusion matrix here. Now there are a couple of things going on in here. One of them is that adding variables doesn't always necessarily increase the accuracy score. The other thing going under the hood is that, well, when we did this, this train test split is not guaranteeing that we're getting the same splitting in terms of selecting the data, because there is some randomization inherent here. Meaning if you do another test split, you would expect to have something different here in terms of outcome, because it's splitting the data randomly every time. So usually what we do this train test split many times, and then we do split the data into a number of sets of different sizes, and then we choose, for instance, 10 sets, and then we choose 9 sets for training, 1 set for testing, and then we repeat the same thing again, varying the testing data set to be the second, third, fourth, and so on. And this is called cross-validation. We're not going to do cross-validation here, but the important thing to understand here is that cross-validation makes the model less sensitive to randomization. Of course, if we want this to be consistent across the two experiments, we probably want to provide some random seeding here so that the testing is the same across the two experiments here. So what I'm going to do here, I'm just going to provide a random state so that I am sure that I'm getting the same observations in the testing and the data. I'm going to just use a random state of 4 here. Oops. So that's basically the previous experiment. And here, so we get to 64% now. In the new experiment where I added the variables, I'm going to add a random state of 0 again. So I'm sure I'm getting the same observation combinations in the training and the splitting data. And I'm going to predict, and the accuracy is 56%. Now again, adding these variables did not improve then the performance of the decision tree. It made it kind of less accurate. So this is something important to keep in mind when we do feature selection. It's not only important to make the model more parsimonious, but many often it's important to make it more performing. So what I'm going to do next, I'm just going to do some kind of model pruning, some feature selection, in order to make the model more parsimonious and hopefully improve the accuracy score. So I'm going to recreate my decision tree, creating a new decision tree classifier. And this time I'm going to add 2 hyperparameters. One of them is the maximum number of features, so I force my decision tree to use the 4 most important features in the data. And the second one, I'm going to constrain the maximum number of leaf nodes. I don't want to have more than 10 leaf nodes. I can also constrain the depth of the tree as well. So this will make sure that I only use 4 features and I don't grow a very large tree. Then I'm going to fit the X train and the Y train. Once I do this, I'm going to fit using the testing set, and then I'm going to evaluate the accuracy score. And you can see that it has improved from almost 10%, more than 10%, from 56% to 68%. Let's take a look at the confusion matrix, and you can see that the tree is now less confused about the first category, but it did not improve equally well in the second category. In the second category, which are baby of normal weight, it's more confused now. So overall, it's more accurate, but it's making more mistakes on the second category. This is something, again, we have to make a decision about whether, false positive are less important or than false negative. That's something also to make a decision about when we look at the confusion matrix versus looking at the accuracy score. Now in this tree, if we print the tree, this tree should be more parsimonious than the initial tree. So I'm going to just copy this piece of text here. And if you can see, it's a much more parsimonious tree compared to the initial one.